As you're probably well aware, most games don't show you their entire world at once. It is much more common to only show a small part, usually what's right in front of the main character, and then to move around the world using some form of panning or scrolling motion. So if you don't intend to make your game world a single static page, you need a way to move around it as well. Better still, it would be ideal to encapsulate the scrolling, rotating, and zooming behavior in a handy and reusable mechanism. The concept often used is known as the virtual camera, or simply the camera. Like its real-world counterpart, the virtual camera can be moved around, rotated, and it can zoom in and out. Following the entity component design pattern, we shall create a camera component. This way, in order to scroll, rotate, or zoom into the scene, we shall simply move the camera's entity in the world. In order to draw any object in the scene, we must first calculate its position and orientation relative to the camera. This is done by multiplying it by its model, view, and projection matrices. In this equation, the view matrix is simply the inverse of the camera matrix. Building on our earlier work with the transform inverse, we simply wire up a way for our virtual camera's entity transform to be used by the game renderer. Now that we have a fully functional camera in our world, we need a way to make it move around. The one we'll be implementing is the commonly used mouse-controlled top-down panning and scrolling mechanism, known collectively as the Real-Time Strategy or RTS camera. Typically, the mouse's input data comes in the form of events. In order for our camera controller to move the camera, it needs to be on the receiving end of these events. First, we make our game class a listener to mouse, mouse motion, and mouse wheel events. Next, keeping to our main design pattern, we create a new component, simply called a mouse listener. Finally, as each event is fired, we need to have our game search the scene for all listeners and call the appropriate event handling function. Towards this end, we first need a way to traverse the scene. We can construct this traversal mechanism in a few ways. The simplest way is to write a recursive traversal function for a mouse event, and then copy and paste this code for every other. This is, of course, wasteful, and can cause maintenance issues down the line. Instead, we'll design the recursive traversal code so that it always traverses the scene, but then does something different based on the situation. The design pattern we chose for this is known as the visitor. In this case, each mouse event will use the same scene traversal code, but with a different visitor in tow. The mouse pressed event will have a pressed visitor, the mouse moved, a moved visitor, and so on. Along the way, we'll be taking advantage of two advanced programming paradigms. One being the use of generics, which is similar to templates in C++. The other is the lambda expression, where instead of writing a whole new class just to implement a single visitor function, we can inline this by just writing in its place. With our mouse-controlled camera movement hooked up and working, we move on to zooming. To achieve this, we'll be using the mouse wheel. And finally, just to add a touch of polish to the camera behavior, we'll add a bit of lerping or tweening into its movement. A lerp is short for linear interpolation, where instead of instantly moving to a position, the camera will smoothly transition to or lerp towards it. This makes the camera way less choppy and overall gives a much more pleasing effect.